Emergency lighting in power plants is governed by several key regulations and standards to ensure safety during power outages. The National Electrical Code, or NEC, specifically Article 700 and Article 500 covering emergency and standby power systems, provides guidelines. IEEE Standard 485.2020, which is the recommended practice for the design and installation of electrical power distribution systems for industrial and commercial facilities, offers further recommendations. NFPA 110.2023, which is the standard for emergency and standby power systems, is another crucial standard. These regulations outline specific requirements for lighting levels and duration. Emergency lighting must provide a minimum illuminance of 1 foot candle, or 10.76 lux, on the floor and 0.5 foot candles, or 5.38 lux, on vertical surfaces. The lighting must be maintained for at least 90 minutes after a power outage. Emergency lighting should be installed in all critical areas of a power plant, including firstly control rooms, secondly turbine halls, thirdly boiler rooms, fourthly fuel storage areas, fifthly switchyards, sixthly emergency exits, and seventhly first aid stations. Several types of emergency lighting systems are commonly used. Battery-powered luminaires provide backup lighting during power outages. Integral battery luminaires combine a light fixture and a battery backup into a single unit. Central battery systems supply power to multiple luminaires from a centralized battery bank. Regular testing and maintenance are essential for ensuring the reliability of emergency lighting systems. Emergency lighting systems should be tested monthly, and an annual functional test should be conducted. Batteries should be tested and replaced according to the manufacturer's recommendations. Luminaires should be cleaned and inspected regularly to ensure proper operation. Other important considerations include reliability. Emergency lighting systems should be designed for high reliability and redundancy. Illumination should be glare-free and not impede vision. Luminaires should be easily accessible for maintenance and replacement. The systems must comply with all applicable safety codes and standards. Batteries must have sufficient capacity to provide backup lighting for the required duration and maintain their charge over extended periods. Luminaires and batteries should operate effectively under extreme temperature conditions. Additional regulations may apply, such as those from the Occupational Safety and Health Administration, or OSHA, and the Nuclear Regulatory Commission, or NRC, for nuclear power plants. These standards ensure that emergency lighting provides adequate illumination, is reliable, and is properly maintained to ensure the safety of personnel during power outages in power plants. The NEC Article 700 covers emergency systems. These systems are intended to supply illumination and power essential for safety to human life. These systems activate automatically when there is a failure of the normal power supply. The NEC also specifies which classes of locations require emergency lighting, including firstly hospitals, secondly transportation facilities, thirdly hotels, fourthly theatres and other places of assembly. Article 700.12 covers the sources of power used for emergency systems. These sources include storage batteries, generator sets, and uninterruptible power supplies, or UPS. Storage batteries must be suitable for emergency service, able to maintain voltage under load, and have adequate capacity and rating for supplying and maintaining the total load for a minimum of 90 minutes. Generator sets must be driven by a prime mover suitable for emergency service and be equipped with an automatic transfer switch. The generator must have sufficient capacity and be started automatically upon failure of the normal power supply. UPS systems must be designed and installed to provide power. NEC Article 700.16 discusses the illumination levels, stating that emergency lighting facilities must be arranged to provide initial illumination. Article 700.26 covers the testing of emergency systems, requiring that the authority having jurisdiction conduct or witness a test on the complete system upon installation and periodically afterward. The test must include the operation of the transfer equipment and the demonstration of the emergency source. Article 700.10 talks about wiring of emergency circuits, specifying that the wiring must be kept entirely independent of all other wiring and equipment. Wiring for emergency circuits must be designed to minimize the hazards that might cause failure due to fire or other causes. IEEE Standard 485 provides practices for the design and installation of electrical power distribution systems. IEEE 485 discusses the importance of reliability and availability of power systems. The standard recommends performing power systems studies to ensure system reliability. IEEE 485 covers the selection and application of electrical equipment, including switchgear, transformers, and cables. It also addresses the coordination of protective devices to minimize system downtime. Section 9 covers the standby and emergency power systems. This section provides recommendations for the design, installation, and testing of emergency power systems. It addresses the sizing of emergency generators, the selection of transfer switches, and the coordination of protective devices. NFPA 110 provides requirements for performance of emergency and standby power systems. NFPA 110 addresses requirements for the installation, maintenance, operation, and testing of emergency power systems. Class defines the minimum time in IOs for which the emergency power system is designed to operate at its rated load without being refueled or recharged. Type defines the maximum time in seconds that the emergency power system will permit interruption of the load. NFPA 110 specifies the location of emergency power supply systems, including the generator, transfer switch, and storage batteries. These locations must be protected from hazards such as fire, flood, and vandalism. The standard requires that emergency power systems be tested regularly to ensure they are ready. These tests include monthly inspections, annual load bank tests, and 5-year functional tests. These tests must verify the system's ability to start automatically, transfer loads, and operate under load conditions. OSHA regulations cover safety requirements for workplaces, including emergency lighting. OSHA requires that all workplaces have adequate lighting to ensure the safety of employees. OSHA requires that exits be adequately lighted. Nuclear Regulatory Commission regulations cover the design, construction, and operation of nuclear power plants. NRC requires that nuclear power plants have emergency lighting systems to provide adequate illumination. The purpose of emergency lighting is for safe shutdown and evacuation during abnormal conditions. Emergency lighting systems at nuclear power plants must be designed and maintained to provide reliable operation under conditions such as loss of off-site power, earthquakes, and fires. The reliability of the emergency lighting systems is paramount. Redundancy, which is having backup systems, ensures that failure of one component does not disable the entire system. High-quality components that can withstand harsh environments contribute to overall reliability. Proper design ensures that the emergency lighting system can handle the specific demands of the power plant environment. Factors to consider in design include the size and layout of the facility, the location of critical areas, and the potential for environmental hazards. Regular inspections identify potential problems. Maintenance includes cleaning, bulb replacement, and battery testing. Inspections and maintenance ensure that the system operates when needed. Illumination should be glare-free and not impede vision. Batteries must have sufficient capacity to provide backup lighting for the required duration and maintain their charge over extended periods. Luminaires and batteries should operate effectively under extreme temperature conditions. The design of emergency lighting systems requires careful consideration of several factors. The first consideration is ensuring that the system meets all applicable codes and standards such as the NEC, IEEE, and NFPA standards. Secondly, the location of emergency lighting must be strategically planned to provide adequate illumination in critical areas such as control rooms, turbine halls, boiler rooms, fuel storage areas, switchyards, emergency exits, and first aid stations. Thirdly, the type of emergency lighting system should be selected based on the specific needs of the power plant. Battery-powered luminaires, integral battery luminaires, and central battery systems each offer distinct advantages and disadvantages. Fourthly, the reliability of the emergency lighting system is paramount. Redundancy, high-quality components, and proper design are all important factors in ensuring reliability. Fifthly, regular testing and maintenance are essential for ensuring that the emergency lighting system is ready to operate when needed. Monthly inspections, annual load bank tests, and 5-year functional tests are all important components of a comprehensive testing program. Sixthly, compliance with all applicable safety codes and standards is mandatory. Power plants must adhere to regulations set by organizations such as OSHA and the NRC, particularly for nuclear facilities, to ensure the safety of personnel and the integrity of operations during emergency situations. Seventhly, in designing emergency lighting systems, it is essential to account for environmental conditions such as extreme temperatures, humidity, and the presence of corrosive substances, ensuring that luminaires and batteries are selected and installed to withstand these conditions without compromising performance or longevity. Eighthly, accessibility of luminaires for maintenance and replacement is a key consideration, as easy access reduces downtime and ensures that the system can be promptly restored to full functionality after repairs or component replacements. Ninthly, the design should minimize glare and provide uniform illumination across the designated areas, which enhances visibility and reduces the risk of accidents or errors during emergency situations, contributing to a safer environment for personnel. Tenthly, the selection of battery capacity should be based on a thorough assessment of the required duration of backup lighting, ensuring that the batteries can sustain the necessary illumination levels for the entire emergency period, with consideration for potential extensions due to unforeseen circumstances. 11thly, the design process must incorporate considerations for charge retention capabilities of batteries, particularly in environments where power outages may be infrequent but prolonged, ensuring that the batteries maintain adequate charge levels over extended periods of inactivity to provide reliable backup power when needed. 12thly, the design of emergency lighting systems should integrate seamlessly with the overall power distribution and control systems of the power plant, allowing for automatic activation and transfer of loads during power outages, while also enabling manual override and control for specific operational needs. 13thly, it is imperative to establish comprehensive documentation, including design specifications, installation records, testing protocols, and maintenance schedules to ensure traceability and accountability throughout the life cycle of the emergency lighting system, facilitating regulatory compliance and effective management of the system. 14thly, the design process should involve collaboration with relevant stakeholders, including electrical engineers, safety officers, maintenance personnel, and regulatory authorities, to gather diverse perspectives and expertise, ensuring that the emergency lighting system is tailored to the specific needs and operational requirements of the power plant. 15thly, the emergency lighting system should be designed to be scalable and adaptable to future changes in the power plant's infrastructure or operational requirements, allowing for easy expansion or modification of the system to accommodate new areas, equipment, or safety standards without compromising its performance or reliability.